All right, Algebrites, on this beautiful day, what we're going to do is look at what's called family of functions. So our goal for today is to analyze the transformation of graphs. So that's going to be interesting to figure out what the word transformation means. So one key thing that we need to know before we can do transformations is some basic graphs, what they basically look like. So when I graph the function f of x equals x, you just get a straight line. We call that a linear function. If I plug this into my calculator, I get f of x equals x squared, and I get this shape right here. This has a special shape. It's called a parabola, and we call the function a quadratic. So a cubic does look like this. So the square root we see here, square root does this, and then the inverse looks like this. And this one here, the inverse square, looks like an Atari symbol. Last two, absolute value and exponential growth. So as we see the absolute value, which we're going to spend a lot of time with absolute value, and we're going to spend a lot of time with the quadratic later on this year. But each one of these is what's called a parent function. A parent function. So textbook definition says this. A parent function is the simplest form of a function that forms a family. So anytime you have a graph that has a straight line with a bounce off it, well, a straight line and bounce to a straight line, that's going to be an absolute value. It might not always bounce at 0, 0. Anytime you have something that flatlines one direction but increases infinitely in the other direction, that's going to be an exponential growth. Anytime you have something that's a straight line, then it's part of this family. Anytime you have a curve that is this way or this way, then that's going to be part of this family. So each one of these is the parent because it's the simplest form of this shape when you graph it. And the function itself is the simplest form. There's nothing multiplying it, there's nothing dividing it, there's nothing adding it, there's nothing adding inside. All it is just a number squared, and that's it. So parent functions each one of these are very common parent functions, and each one of these will create a family of lots of little functions. Now on the next page, what you're going to do is go to airmath.net, and what we're going to do is play around a little bit with different functions. So read along here. In this lesson, we're going to explore how to move or translate or compress, which we call transform, the graphs of different functions. So we're going to select these dots in Desmos. So I'm at desmos.com, and you can get that link from airmath.net. And we're going to click this triangle right here to open to see what happens here. So let's see what happens with each one of these. So here I am. I have a linear function, which is y equals x, and we see that it simply just graphs like this. And I'm going to see what happens when I move a slider around a little bit here. So notice that moving the m, in other words, multiplying the x, what it does is stretch out my function. It's like I grab the function and I stretch it up and down. This one here is kind of like I'm compressing the function down to be flat. Now, notice here that the k, if I adjusted the k, which the k is being added, notice all I'm doing is taking my function and shifting it up, or down, All right, so we see that adding something to the function can move the graph. Multiplying the function can change it as well. So let's look at the quadratic function here. Quadratic function looks like this. This is called a parabola. And notice I have something multiplying. Notice the parent function here is just x squared. It's just something squared. The h is being added or subtracted on the inside of the parentheses. And k is outside the parentheses. And a is also outside the parentheses. And it is, I'm multiplying the square part. So let's see what happens here. So if I were to adjust the h, notice what happens here. As I adjust the h, all it does is move things left or right. My purple is moving left or right. So I'll pause that for a second and bring it back to home plate there. Now, what happens with the k? If I were to adjust the k, which is adding to the outside, notice as I add more, the whole function just moves up. And as I subtract, the function moves down. Next up, the a. What happens when I adjust the a? It's like I pull really tight, or I push it down, and as I push down, it opens up quite a bit, and then it can flip upside down. So the a, the multiplication in the front, makes it move squash or pulls it tightly. All right, next is a sine function, and the sine function looks like this. It's just called sine of x, and as you can see, I have the same thing. A is multiplying it, h is on the inside, and k you can't see here, but it's on the outside, and it's being added or subtracted. So what happens with h? If I were just to adjust the h, all it does is take my function and move it left or right. All right, and as I adjust the k, which I'm adding on the outside, it just opens, moves it up or down. And continuing on, as I adjust the a, which is the multiplication part, it just makes it larger or squashes it down to smaller or flips it upside down. There's one more here, b. What b does is adjust whether it's going to be tighter or not. We're not going to touch b very much. So the h, which is on the inside next to, we're adding to the x, so it's kind of like an x plus an h, like that, or x minus. What it does is that it shifts left or right. The k, which we saw was outside the function, so in this case it's a c, but the point being is that it's outside the function. Here's my function, and I'm adding something outside of the function. What that does is it does a shift also, and that's up or down. And then lastly, the a, which we had in front of, just like we have down here, in front of the function, it multiplies the function. So notice the shifting are adding. You either add inside or you add outside to adjust. Here, if you're multiplying outside, then that is going to do what's called a compression, and more specifically, let's say a vertical compression or stretch. Vertical compression or stretch. A vertical reflection. In other words, I can make the whole thing flip. If I keep compressing it, it'll eventually flip upside down. And then I can stretch it upside down. So each of the transformations, it's any change to the parent function, we can shift it left or right, up and down. We can compress or stretch it, so squash it. We can also reflect it. We can flip it upside down or left and right. So let's just follow along here. We're going to take each one of these from above here, and we're going to place them in the empty containers. So it's probably easier just to start here and then go over to horizontal translation. We noticed up here that whenever I adjusted the inside, the h which was inside, I can make it translate left or right. I can shift it left or right. So this right here, f of x plus h. So I'll zoom in there. So we get f of x plus h. So notice the plus h or the minus h is inside the function. Next, what happens when I add or subtract outside of the function? Well, if I add or subtract outside of the function, that is going to be a vertical translation. So that's how I shift it up or down. Next, a vertical stretch. So if I wanted to pull this thing taller or smaller, all we do here is we need to multiply by a on the outside, and a's got to be bigger than 1. So a can be a 1.2 or 1.3. What it does is it scales. That's what's called the scale. It scales it. Vertical stretch. So in this case here, we're going to say that a times f of x. But a has to be greater than 1. And that stretches it. You grab it, and it takes it from here to more like that. All right, the other option besides vertical stretch is that you can do a vertical compression. a vertical compression. And a compression means you squash it. So that is going to be here where I have a times f of x, where our a is between 0 and 1. So it's like a 1/2, 1/3, 0.2, something like that. So again, it's the same as the other one, but a is a different type of number. A has to be between 0 and 1. Something like this. If I said 1/2 of f of x, that's going to squash the function, compress it. All right, the last thing we have is we have reflections. And that goes here, reflection. And we've got two types of reflections. One of them is reflecting left or right, and one of them is reflecting up or down. So this one here is a horizontal reflection. When you are inside the function, you take the opposite. When I'm outside the function, it's a vertical reflection. In other words, I flip it upside down. Pretty much that's what vertical reflection does. We actually want to consider absolute value here, because what we're looking for ultimately is the largeness of the number relative, like how far away from 0 it is. In this situation, family of functions. So given a parent function f of x. Now remember, the parent function could be linear. Like I could just say y equals x. I could say y equals x squared, like any of these parent functions. And depending on what you do to that function, it's going to adjust the graph. So let's see what each one of these does. The a here in the front does one of three, not one of three things, does multiple of three things. Number one, it could be a vertical. It is always vertical. It's either a stretch or a compression. At the same time, it could also be a reflection, a flip. So outside is dealing with vertical, outside the function, not inside the parentheses, outside the function. Which means since plus k is outside the function, this also is vertical. But this is a vertical shift. And the key is positive goes right, negative goes left. Now, anything happening inside the function is horizontal. I'm not saying horizontal for because of the h. I'm just saying horizontal, anything that happens inside. And technically, there's something else there. We could also multiply by a scale there to increase or compress it. But we don't focus so much on that. So in this case, h is going to be a horizontal shift. And this one is slightly different. Positive means left and negative means right. So it's opposite of what you see. It's the opposite of what you see for horizontal. So we can summarize this whole thing just by making a little quick chart here. Here we have something happening inside the function, outside the function. We have a product going on or a sum, an addition going on. So whenever it's inside, we see it's going to affect the horizontal. Whenever it is outside the function, it's going to affect the vertical. Any multiplication will always scale it. It'll compress or stretch, also can reflect. And any addition or subtraction is going to be a shift, a translation left or right. So if I am adding inside the function, we see it's a horizontal shift. One focus we want to point out here is that this one is not used very often. It's there, but it's not. It's a little bit more complicated to analyze. So for our purposes in this class, we're going to skip mostly that one there, okay? So let's practice a little bit. We want to identify the parent function and then describe the transformation. So the parent function is this. Y equals I'm going to ignore the 3 and just say x squared. Y equals x squared. So what's happening here? Well, I see that there is a 3. I see that there is a multiply by 3. So if I go up to here, it's multiply by 3, and it's happening outside of the x squared. Look, it's outside the x squared, as opposed to this. Like inside, like that would be inside the function, where the 3 is being squared too. So we're saying here it's happening outside of the x squared. So because of that, it is an outside multiplication, so it's a vertical scale. So let's just break down step by step here so we can analyze it. This here is my a, and it's greater than 1. So we know that it is going to stretch. So because it's outside, it's vertical. Because a is greater than 1, it's a stretch. And I just tell by what factor? By a factor of 3. In other words, triple the dots. Wherever the dots are, wherever the plots are, we triple the height, the altitude of that. Just for clarification, I do want to point out that the a, when we're considering the a, we're actually considering more like the absolute value. So I might want to make that change above, up here, or on the previous one. So looking at the next one here, the parent function is y equals x. Because I have an addition occurring, we know it's going to be a shift or a translation. And because it's happening outside, we know that because there's no parentheses. Like if there were parentheses, we might say inside. Because it's outside, it's a vertical. So the end result here is this. A vertical shift up 5. All right, let's look at C here. C is going to tell me a couple things. I see the parent function. Number 1, the parent function is called a cubic. So it's just x cubed. Next, I see a negative in the front, which means I am going to reflect. So this one is a vertical reflection. I'm going to write to show you an alternate way to say that. It might you might see it written in a different way. So vertical reflection is one way to call it, but another might say reflect on the x-axis. All right, next, the half. Because it's a multiplication, we see it's going to be a scale. And because this a is between 0 and 1, we know that it is going to be a vertical compression. We squash it down a bit by a factor of half. So the full description of this would be the parent function is a cubic, y equals x cubed. The negative tells me it's a vertical reflection, and we also are going to compress this function by a factor of 2, or 1/2. All right, let's complicate things a little bit. We have lots of stuff going on in this one. Lots going on. First off, the parent function. That one might be a little tricky to find, but it's the simplest form of what I see. So we see that. Just ignore all the stuff that's happening around it, and the parent function is y equals f of x. But Swenson, f of x, what is it? And the answer is we don't know. There is no basic shape f of x. It's just the name of a function. It could be a squiggle, it could be a line, it could be whatever. It's just a basic name. Next, I need to start interpreting what's happening here. The negative means I am going to vertically, it's going to be a vertical reflection. On top of that, the 2 here means I am going to also vertically stretch it by a factor of 2. Next, I have 2 things going on. I am shifting it up and down or left, up or down, and left or right. So I'm going to say both of those at the same time. I'm going to say I'm going to shift, in this case, up 6 and right 3. So a skill that you're going to have is you have a given function, and what you want to do is translate that. So we're not translating from the parent function, we're translating from a given function, okay? So the given function here is 6x minus 2. And I want to do a vertical. So vertical compression means I am going to multiply outside. So here's my original function, 6x minus 2. So if you put parentheses around it, then the vertical compression is happening outside of this. So I put the 1/3 in the front. Next, if I want to make it reflect and I change this to x-axis, all you have to do is reflect and I throw a negative in the front. Now, this is the most simple form of what we do, but technically I can use the distributive property to clean this up. So I'm going to go ahead and rewrite this into slope-intercept form. Slope-intercept form. So that's going to look like this, where the 1/3 gets sent into both of those. The negative 1/3. So the final result would be this. Y is negative 2x plus 2/3. We'll clean that up. Plus 2/3. And where did that come from? The negative times the positive. 1/3 of 6 gives you negative 2. And then negative times negative is positive. And 1/3 of 2 is 2/3.